Okay, we'll start with today's quote. Wealth, like happiness, is never attained when sought after directly. It comes as a byproduct of providing a useful service. Usually, wealth and happiness, whenever you try for it, you strive for it, normally you will not get it. It will go away from you. And like as people say, rat race, you have to be running to get it. But if you are providing service to anybody, automatically this wealth and happiness comes as a byproduct. You need not strive for it. It automatically comes to you by itself. Okay, and today is the birthday of Boris Borisovich Golitsyn. He is a Russian physicist and seismologist who developed scientific methods and instruments for earthquake observations and mineral prospecting. His early studies were in molecular physics, mathematical physics, and electromagnetism, and from 1899, his interest turned to seismology. In 1906, he invented the first effective electromagnetic seismograph and continued to improve it. It had a pendulum carrying a coil of insulated wire around a magnetic core fixed to the ground. The small current generated in the coil by relative motion caused by earth tremors is amplified to operate a pen recorder. The part of the Earth's mantle at a depth of 400 to 800 kilometers, in which seismic waves travel rapidly, is named. mm, Okay, I think this lower one I could not see. Okay, so he is Galitzin who has found seismograph. And today we are going to discuss about incompressible Navier-Stokes equations. And till now, if you just see what are the things we have done, right? So we have solved first elliptic equations of the sort like del square u equal to 0 or del square t equal to 0, which is some uxx plus uyy equal to 0. So these type of equations we have solved means in the general equation, we have to know how to handle diffusion term or the viscous term. So how to handle this particular viscous term we understood by seeing what are the various solvers for elliptic equation. And then we have seen parabolic solvers. So for this we have taken equation like ut is equal to mu xx or tt is equal to some alpha tx. So these type of equations we have solved using various teams. So this tells you how to handle unsteady term. Right? So this unsteady term how to handle we have learned from this. And then we have gone to the hyperbolic solvers. So where we have taken ut plus aux equal to 0 or then nonlinear ut plus uux equal to 0. So this tells you how to handle convection term, right? And then we have taken the Berger's order, where I have like this, which has unsteady term and the convection term and the diffusion term. All the three terms we have. Okay, so this is the way we try to learn how to handle those particular terms, unsteady term, convection term, and diffusion term. But till now, we have taken only a single equation. So hereafter, we deal with simultaneous equations. Simultaneous, not only simultaneous, but linked equations, right? So this is the way we are going to do. So if you just recollect what are all the basic assumptions for Navier-Stokes equations. So can you just recollect? One is continuum, right? And another is okay, no chemical or nuclear reactions. Okay, and then what else? Homogeneous and isotropic, and next, anything else? Okay,
Relativistic mechanics.
Optimal
yeah,
hypothesis.
okay, or finite mass and velocities, right? If we have very high velocity, we have to go for relativity. If mass is very negligible or something, we have to go to quantum mechanics like that. So these are the general assumptions that we have made. Okay, now we are going to deal with incompressible flows. Okay, so what is the assumption for incompressible flow?
Like density variations are minimal.
Rho is equal to constant. Okay, so that's it. And we also made an assumption, and even previous one also we can write it, and mu equal to constant means you take Newtonian flow. This is incompressible. Okay, and what is the characteristic of incompressible flow? The incompressible flow means, uh, can you tell me what is the
Uh,
sonic velocity in incompressible flow?
Less than 0.3 years.
It tends to infinite. M tends to 0. A pure incompressible flow means Mach number 0 or sonic velocity infinite. So that is actual incompressible means. But you can assume it to be incompressible uh, if m less than zero point 0.3. We can approximate the flow to be incompressible. Okay, and another some of the characteristics are uh, energy equation gets decoupled from continuity and momentum equations. Okay, what do you mean by this? I need to solve energy equation only if we are interested in energy. Sorry, not energy.
Temperature, sir.
Temperature, yes. So if we are interested in temperature, then we solve energy equation. Otherwise, you need not solve energy equation at all. So that is why it happens. In compressible flow, we have to solve energy equation. But in incompressible flow, unless we are interested in temperature, we need not solve. Like civil engineering people, they don't bother about energy equation. They just solve the continuity and momentum equations. And why we have this trouble? Okay, and how it is decoupled? Okay, and what is the connection between these two and how it is decoupled? continuity momentum and energy equation, how they are coupled.
Coupled by pressure, no, sir. Momentum and energy equation.
Means, okay, energy equation cannot be solved unless you solve continuity and momentum equations. Okay, but in compressible flow, energy equation is to be solved for continuity momentum equations. That's why they are coupled. But here, I need not solve energy equation to solve continuity and momentum equations.
Yes, sir.
So temperature, I don't bother, mainly because mu is taken to be constant. Okay, if it is a function of temperature, then I have to note what is temperature to get what is viscosity. Am I clear?
Yes.
Okay, so actually energy equation, we solve it only if it is needed. Otherwise, we solve only continuity and momentum equations. Okay, so here T normally we don't bother unless it is needed. So the variables are velocity and pressure. Only two dependent variables. And the equations are continuity and momentum. Okay, so dependent variables are velocity and pressure, and the equations to be solved are continuity and momentum. Okay, we don't bother about even equation of state also, because the number of equations to be equal to number of unknowns. Why there will not be equation of state?
We know rho and we don't want T, that's why.
No, actually equation of state works only for ideal gases. Okay, at high temperature and low pressure, and also it is mainly for gases. And usually, okay, here also gases may come, but the compressible effects are not there, right? So that's why we don't, equation of state is not valid for incompressible flows. It is only for compressible flows only. Okay, so we have to solve the continuity and momentum equations for velocity and pressure. Okay, so that's why what happens, your memory requirement is very less, because only velocity and pressure I have to solve. The number of variables that I have to store are less. And as I told, if I want temperature, then I can use these pressure and velocity, and then I solve for temperature. Okay. And then people thought actually, okay, solving incompressible, then it's so easy or simple compared to compressible flows. But it is not found to be easy. Okay, what is the difficulty that they have faced is the time step. Okay, what is the problem? So this problem comes with CFL condition. Okay, what is the CFL condition? A delta by T by delta X, current number, should be less than or equal to 1. Okay, so delta T should be less than or equal to delta X by A. And as I told, for incompressible flow, A tends to infinite. Okay, very, very large. Okay, infinite is for very ideal incompressible flow. Otherwise, it is very, very large. So what happens to delta T?
It will be very small.
Delta T tends to 0 means very, very small. Unless you choose very, very, very small delta T, the stability problem will come. So what happens is the number of time steps or the computational time tends to infinity. Okay, so this is the problem comes. Okay, when is this stability condition is required?
If we are time marching,
Mainly for explicit methods. Am I right? So usually we cannot use explicit methods to solve incompressible flows. So we have to use implicit methods only for stability requirement. Okay, so this is one of the main thing that we have to remember. Okay. Hmm. Okay, now another problem. Okay, and we have the continuity equation. What is continuity equation now? Okay, I take 2D. Okay, so what is the continuity equation for 2D incompressible flow? Dou E by dou X plus dou V by dou Y equal to 0. Okay, this is the continuity equation. So the complete continuity equation is rho T, dou rho by dou T plus del dot rho V equal to 0. Okay, so this is the complete continuity equation. But because it is incompressible, rho T is 0 and this rho can be taken out. So del dot V equal to 0 is the continuity equation for the incompressible flow. So means Ux plus Vy plus Wz equal to 0. So because it is 2D, only this will come. Ux plus Vy equal to 0. So this is the continuity equation. And what is the momentum equation? Because it is 2D, I will have two momentum equations. Okay. And okay, in general, if I write dou V by dou T, conservative form, plus del dot dV is equal to minus 1 by rho del P plus mu del square V. Okay, this is the equation. So if I have 2D, I will have two momentum equations, dou U by dou T and dou V by dou T. Two equations will be there. And U can be calculated from the X momentum equation and V can be calculated from the Y momentum equation. Okay, now the problem here is, okay, so I will have dou U by dou T plus dou V by dou X equal to 0. Sorry. And dou U by dou T plus dou by dou X of U square plus dou by dou Y of UV equal to minus 1 by rho dou P by dou X plus mu into Uxx plus Uyy. Similarly, dou V by dou T plus dou by dou X of UV plus dou by dou Y of V square is equal to minus 1 by rho dou P by dou Y plus mu into Vxx plus Vyy. Okay, like this we have the equations. And okay, if you do time marching or whatever it is, so you will get U from this equation and V from this equation. And now what are the dependent variables? U, V and T. Okay, now can you understand what is the problem now? Anybody?
there are three equations and three variables, right? What's the
Okay,
problem?
These are the three equations, continuity and two momentum equations.
Yes.
And the variables are u, v, and p. Now, what is the difficulty in solving for this? So as I told, by time
On
matching, I can get u from the x momentum equation, v from the y momentum equation. And what is the equation left is the continuity equation. And what is the variable left is the pressure. And I have to solve pressure from the continuity equation where there is no pressure at all. Am I clear what I am talking?
Yes.
So this is the problem. And when you solve compressible flows, so I told you solving, I have a solution vector, okay, dou u by dou t, that u is the solution vector where I have rho, u, v, p, and that internal energy or temperature will be there. And so you can solve each variable from each one equation. Okay, so there is no problem at all. But here, x momentum u, y momentum v, just like compressible flow, there is no problem. But now the third variable p is to be obtained from the remaining equation, which is continuity equation, and which doesn't have any pressure there. So I have to somehow introduce pressure into the continuity equation. So I have to do some mathematical manipulation, okay, and so I have to get p from continuity. Okay, so to introduce, we have to introduce pressure into continuity equation. Okay, so this is what is called as, we are going to do that. So we derive what is called as pressure Poisson equation. Okay, so that we will see. Okay, this is one of the main difficulty that you face. And the methods of solving. In compressible flows, there are two methods. One is using primitive variable formulation, and another is omega psi formulation. So in the primitive variable formulation, again, I have two types. One is called as regular grid, and another is called as staggered grid. So we will see what is that staggered grid. So in the regular grid, there are two methods we are going to discuss. One is artificial compressibility approach, and another is Frank-Nicholson method. And in the staggered grid, we are going to deal with two methods. One is called MAC method, which is marker and cell method. And another is simple. This is very, very popular. And this is what is called as semi implicit method for pressure linked equations. Okay, so simple and its variations. There are some more methods of as a variants of simple. Okay, so these are the various methods which you are going to deal with in so in omega psi formulation. So we will just compare this primitive variable formulation and omega psi formulation. So in the primitive variable formulation, the equations are, if you classify them, mixed, elliptic, parabolic. Okay, so why it comes? Because actually the momentum equations, they are like parabolic, because I have dou u by dou t, dou v by dou t. Usually unsteady equations behave like parabolic equations, as I told, because it moves, time moves in only one direction. And the elliptic, because of the continuity, as I told, we convert it to, we are going to get what is called as pressure Poisson equation. So mixed elliptic parabolic equations we will get. Okay, so these are coupled equations to be solved simultaneously. Okay, and these can be extended to 3D. And the main difficulty comes uh, in pressure boundary condition. The prescribing pressure boundary condition is almost many times is not possible. And so this is to be handled. Okay, this many times this is handled by what is called as that simple approach, or MAC approach. So using staggered grid. Okay, this we will discuss later. Okay, so to handle the pressure boundary condition, which is not known always, so then we have to go for what is called as the staggered grid approach. Okay, this is about primitive variable formulation. But if you just recollect about omega psi formulation, so what are the equations that will be solved? Omega, that is vorticity transport equation. Which is omega t plus del dot d omega is equal to mu del square omega. Okay, so the advantage, mainly why we have derived vorticity transport equation, is to eliminate pressure from the equation. So if you remember, we have taken the momentum equations, right? We have taken the cross product of the momentum equation. We got the vorticity transport equation by taking curl of momentum equation. So we got the vorticity transport equation. So where we del cross del P became 0, so we got away from the pressure term. Okay, so this is the equation, and this is parabolic equation. And the one important thing is, here I have to solve omega equation and psi equation, and these are decoupled. Omega and psi equations are decoupled. Okay, what do we mean? As I told, okay, I need, okay, well, right before that I will write stream function equation. What is stream function equation? Anybody?
Dou psi by dou x.
Del square psi is equal to minus omega. Del square psi is equal to minus omega. This is the stream function equation. If it is irrotational, then del square psi equal to 0. This becomes elliptic equation. And now this is also elliptic equation also. This is Poisson equation. So here if you see, this is not having no psi here. I need not know psi to solve vorticity transport equation. But to solve psi, I need omega. Okay, so the thing is, I can independently solve them. As the energy equation I told, I have to solve that if I need temperature. But continuity and momentum equations are independent of temperature. That's why energy equation is decoupled. In the same way, to solve omega, I don't need psi. So this omega separately can be solved. I need not solve the equation simultaneously. Okay, but if you take primitive variable formulation, continuity and momentum equations, they are dependent on each other. Okay, you cannot solve independently a continuity equation and momentum equation. Okay, because momentum equations contain velocities, and to solve velocities, I have to solve momentum equation. Okay, so they are coupled, and here omega and psi equations are decoupled. So omega solved separately, and psi can be solved later. Okay, so I can have a separate loop for omega equation and then separate loop for psi equation. But when they are coupled, I have to put both the equations in the same loop. Okay, so that is the meaning of coupled and decoupled, and this is elliptic. So a parabolic equation separately and elliptic equation separately I have to solve. And here also I don't have pressure, right? So again, for omega psi formulation, I have to derive a pressure equation which uses omega and psi and get me thing. Or after solving psi, here what happens is in omega psi formulation, solve vorticity transport equation for omega and solve stream function equation for psi. And once you get psi, u is equal to psi y, v equal to minus psi x, and get velocities. And using the velocities, solve for pressure. So I have to derive a pressure Poisson equation here also. Okay, we will see the derivation of pressure Poisson equation after this. Okay, so just we will go to the PPTs. I will show you those equations in different forms. Okay. Okay, the assumptions we made are continuum, no chemical and nuclear reactions, reasonable mass and velocities, homogeneous and isotropic, no mass transfer, body forces are negligible. Okay, so for this incompressible. So we have to solve continuity, Newton's second law of motion conservation, and first law of thermodynamics energy conservation. And constant density flow, mass and Mach number tends to 0, A tends to infinity, viscosity is constant, and energy equation gets decoupled from continuity and momentum equations. And velocity and pressure fields are computed by solving continuity and momentum equations. And energy equation is solved if temperature field is needed. And computer storage needed is reduced because of reduced dependent variables. And computational time is too much, as the condition for stability CFL condition leads to very, very small time step due to large A. Okay, so the numerical solutions using primitive variable formulation and vorticity stream function, and here regular grid and staggered grid, and regular grid artificial compressibility method and Crank-Nicolson, and staggered method marker and cell and simple method, and vorticity stream function formulation. We have to solve vorticity transport separately using either FTCS or ADA, and stream function which is elliptic, we have to solve PSO or LSO or ADA, just which we know already. Okay, so different ways of presenting the equations. This is in vector form and also conservative form. And this is in Cartesian form and conservation form. And it is written in combining the convection term and the pressure term. Okay, so it is written like this. This is conservation form in Cartesian form. And if you take non-conservation form, it will become, instead of del dot VV, we get V dot del V. Okay, this is the only difference. Other things will be as it is. Convection term only. So here in the conservation, here dou of U square by dou X will be there. Here U dou U by dou X, V dou U by dou Y will be. So this is the difference you will get in the convection term, and other terms will be as it is. And you can write it in non-dimensional form also. In non-dimensional form, all these becomes non-dimensional, and instead of viscosity, I will have 1 by Reynolds number. Okay, this is the only difference you will get. If you want, I will do it non-dimensionalization. but it's very simple. If you take actually this way, T star is equal to T u infinity by L, X star is X by L, Y star is Y by L, and Reynolds number is rho u L by mu. T star is T by rho infinity square, rho u square. Like this, if you do it, so you are going to get the equations like this. Here, all are non-dimensional form, but to make it easy, I won't write the stars here. Okay, so whether it is dimensional or non-dimensional, you will understand only if there is no density in pressure term and viscosity is replaced by 1 by Re. Okay, then it will become non-dimensional equations. Okay, so this is the way we can write in non-dimensional form. As I told, sometimes non-dimensional form is better to solve. One is because your characteristics get collapsed to very few graphs, and another thing is the values normally, suppose because u infinity is the maximum velocity, so u by u infinity, which is u star, it varies only from 0 to 1. Okay, the range of the values will be narrowed down. So that is another advantage. It is like normalizing. Okay, so when you normalize a particular variable, it will confine to a particular range of values. Okay, so this coming to omega psi formulation, this I have written. I have written in conservation form. Here you can see like this. Okay, this is conservation form. Dou by dou x of u omega, dou by dou y of v omega. But if you write non-conservative form, you will get u dou omega by dou x, v dou omega by dou y. Okay, so this is the way you will get the vorticity transport equation, and this is the stream function equation, and so you can get the velocities from these two. And you can write this in non-dimensional form also. So again here, you will get 1 by Ru. Okay, this is in Cartesian form, conservation form. So this is in different ways, whatever you want, in whichever form you want, you can write. Okay, so when you compare the primitive variable and omega psi formulation, primitive variable, it is mixed elliptic parabolic system of equations which are solved simultaneously. The unknowns in the equation are velocity and pressure. So there is no direct link for pressure between the continuity and momentum equation. And to establish a connection between the two equations, as I told, pressure is not there. So some mathematical manipulations are introduced. So generally speaking, there are two procedures for this purpose. The first is that of the Poisson equation for pressure, which is developed in the next section. And the second is the introduction of artificial incompressibility. So these are the two methods, as I told, we are going to discuss. And specification of boundary conditions and in particular pressure may be non-existent. So to overcome this difficulty, a special procedure must be introduced. As I told, like staggered grid concept is introduced there. We will discuss again that also. And this can be extended to 3 dimensions and it is straightforward. Okay. And we're coming to vorticity stream function formulation. So here these two equations are also decoupled, as I told. Okay, they are decoupled into one elliptic equation, which is the stream function, and one parabolic equation, which is the omega equation. And this formulation does not include the pressure term. Therefore, the velocity field is determined initially, and subsequently the pressure equation, Poisson equation, is to be used to solve the pressure field. And due to lack of simple stream, and this cannot be extended to 3D because stream function doesn't exist for 3D. So you cannot extend omega psi formulation for 3D solvers. Okay, now coming to this pressure Poisson equation, how to derive it is, so this is the conservation form of momentum equation in u direction and the x direction and y direction. So what I have to do is, okay, maybe I will do it. Ut plus u square x plus uv y is equal to minus 1 by rho px plus mu axx plus uy, and then vt plus uvx plus v square y equal to minus 1 by rho py plus mu vxx plus mu. So what I have to do is I have to take the x derivative of the x momentum equation and y derivative of the y momentum equation and add these two. That's what I have to do. So you are going to get first term utx plus vty. Okay, these unsteady terms plus u square okay, and this term can be simplified like this, ux plus vy of t. Okay, by interchanging the order of derivatives, you can get like this. And here u square xx, okay, this one plus this one v square yy plus here uv of xy you will get here, and here also uv of xy you will get. So 2 uv of xy is equal to minus 1 by rho px plus py pxx plus pyy plus here what I will write is mu of like this you will get. Okay, so I will write ux plus vy as some d. Actually, here the doubt comes is ux plus vy may be 0 because continuity equation is ux plus vy equal to 0. But because these are coupled equations, unless I solve the continuity, if continuity equation is solved, ux plus vy is 0. But I don't know what are the values of u and v. I assume some values, so it will not be 0. It will have some finite value, and thus that I will write it as d. Okay, so here I will write this as dt plus u square xx plus v square yy plus 2 uv xy. And if you see, this is that Laplace term minus 1 by rho del square t plus nu times. Now here this can be written as if I combine these two, ux plus vy of xx plus here also ux plus vy of yy. You understand this? Here three x's, I separated it x and double x, and xxy, I have written y first and xx is there. So these two terms will come to this, these two terms will come to this. Okay, so here this will be nu into dxx plus dyy. Okay, so this will become like this, dt plus u square xx plus v square yy plus uv 2 times xy is equal to minus 1 by rho del square t plus nu dxx plus dy, or this is del square d. It will become like this, right? So here this is the pressure Poisson equation. I'll del square p I will take to this side is equal to 1 by rho or rho into, I will write all the other things, dt plus u square xx plus v square yy plus 2 uv xy This means del square like this. Okay, this is the equation. This is what is called as pressure Poisson equation for primitive variables. Because 1 by rho del square p, okay. If I take that side, yeah. I will have negatives for these things, right? So, like this. Okay, we will see this equation is written there. Okay, here x derivative of this is taken, y derivative of this, and this x and d derivatives are exchanged. Okay, so it is written like this. Okay, del square p. Okay, this is written in non-dimensional form. That's why that rho and nu are not written. So rho is absorbed into p, and the nu is written as 1 by RV. Okay, so this is the way you will get the equation, pressure Poisson equation. Okay, so this is the same equation which we have derived here. Okay, this is for primitive variables, and in the same way we have to derive it for omega psi formulation, right? So you go through this derivation, right? If you don't understand, we will do in the next class because the time is over, right? You will do this derivation. So next class we will see how to solve these equations using various approaches, as I told, the artificial compressibility approach and Crank-Nicolson and the staggered grid. All those things we discuss in the next class. Okay, so this is the equation we get for omega psi formulation. This is again del square p is equal to something like this. Okay, so we have to have the pressure Poisson equation separately derived for primitive variables and omega psi formulation. And how this is used there, that also we will discuss when we solve it. Okay, so any questions?
No, sir.
Okay, so we will go for the today's story. We'll just see about Abraham Lincoln. Okay, he is a really inspiring personality, like our Lal Bahadur Shastri and Abraham Lincoln. These two are came with very low poor family. Okay, but initially his uh, position was good. Okay, see, Abraham Lincoln was born in 1809 in a small log cabin in Kentucky. His parents were Thomas and Nancy Lincoln. At the time of his birth, Abraham's father owned extensive farmland and Abraham was able to attend basic education courses. When Abraham was 7, the family moved to Indiana, where the family had a much better life. The prevalence of the milk sickness in the area, however, was the beginning of Lincoln's difficult life. His family was greatly affected by the illness as it took several family members to the grave, including his mother. So this is the tough time he started to have. And the household chores were distributed between Abraham and Sarah, his sister. And some people said that Abraham seemed lazy at this time, refusing to participate in household chores. But later, he learned and contributed greatly to the work around the house and to the family's earnings. And because of these circumstances, Abraham had to stay home to help rather than attend school. So he could not attend school because of this. He had attended only a year's worth of lessons, and his yearning to learn was fresh and alive. He had no choice but to remain at home. So he started to study on his own. He was basically self-taught the rest of his life. He didn't have any basic education. Everything he studied by himself. Even his law degree was a result of intensive self-study only. And Abraham's father remarried a widow with 3 children. Missing his relationship with his real mother, Abraham instantly bonded with his stepmother and would later even refer to her as mother. They moved several more times until Abraham was old enough to go about his own life. He opted to leave his family and travel to New Salem, Illinois. And New Salem played a part in the development of his skills in speaking and persuasion. He worked as a store there and thus came into contact with different personalities every day. He was motivated to learn everything he could about the practice of law. He borrowed books from people he knew as he could not afford to buy his own, but he studied rigorously and later used his knowledge as an avenue to public office. And Abraham Lincoln's path to the presidency was tedious. He served as a captain of a troop of the Illinois militia during the Black Hawk War, and soon after this he started to venture into public office. Although his first try as a candidature of the Illinois legislature failed, you can see sometimes there is a WhatsApp message also. What are the various steps he has failed to before attaining the presidency? And okay, his candidature is failed. He was re-elected thereafter and served 4 full terms in the office. During this time, he perfected his law studies. Attempting to advance his own position failed. However, as he was unsuccessful in his bid for the Congress, he resorted to building a strong foundation for his law practice. He spent more or less 15 years in the business representing everyone who needed a lawyer. The cases he handled ranged from transportation issues to monetary disputes and even murder charges. The challenges in Lincoln's life were not exclusive to his political career alone. His romantic and family life also proved to be a trying department. Abraham was engaged to be married to Anne Rutledge in 1835 when she died of typhoid fever. He ended up marrying Mary Todd, who was from a prominent family in Lexington, Kentucky. Their first scheduled wedding was broken off by the couple after having decided they actually didn't want to get into the marriage. But 2 years later, they ended up marrying each other after all. And he had 4 sons, and he managed to outlive 3 of them. So before he died, actually he has seen 3 of them died before his eyes. The firstborn, Edward, died of tuberculosis at age 3, while the second child, William, died when he was only 11. The fourth son, Thomas, died when he was 18 due to heart failure. Only the third son, Robert Todd, lived to see adulthood and ultimately died at age 2. The times proved difficult for the couple. Mary struggled emotionally and psychologically and was admitted to a mental institution later in her life. And Abraham also suffered from depression, so severe that he spent 6 months confined at home. And the reactivated issues on slavery in the United States had encouraged Lincoln to try to capture another position in public office. His popularity grew as he openly expressed his disagreement with the acquisition and trading of slaves in the country. The birth of the Republican Party further strengthened Lincoln's chances in making to it Senate. He envisioned a world wherein everyone is equal and in which the government favored no specific race. And Lincoln's aspirations captured the hearts of people, and although he was not elected to become a senator, he was as popular as ever, and his name was brought up whenever there was talk about the presidency. Okay, though he became popular, but to become elected, it took very, very long time. Many times he was not selected. As Lincoln assumed his duties as the 16th President of the United States, many opposed his liberal idea of abolishing slavery. His thoughts seemed so radical that 7 states immediately ceded and decided to produce their own country, the Confederate States of America. His term was defined by the advent of the Civil War. At the peak of the war, a total of 7 states united against his leadership and his ideals. The circumstances in Abraham Lincoln's life led to great leadership during the Civil War. As he had always done, he studied military tactics and operations independently to better lead his army. And furthermore, he still insisted on the concept of equality among all men, and later during his term, he finalized the decree that all slaves be freed. If you really read the old novels of English, you can, because we don't know about slavery much, okay, but the way the people are taken from the Africa by boats, I think there is one beautiful novel, Roots. Okay, so you can see about the slavery, and so many years, so many centuries, people are suffered. And with his skill in military operations and his knowledge in political manipulation, the United States won over the Confederate States. It successfully bringing an end of the Civil War ended Abraham Lincoln a second term as president. He addressed his fellow Americans and said that it was time to build up the nation as one of the freedom. He, however, did not live to see the day. Shortly after the end of the war, Lincoln was assassinated while watching a stage play with his wife. Despite the premature end of his political leader's life, the results of his battles are evidently well lived today because now we don't see those things. And America is now the land of the free, where gender and race are no longer measures of social status. Most importantly, and as Abraham Lincoln wished, the United States built a government of the people, by the people, and for the people. So this is a famous quote by Abraham Lincoln, right? The government, any government should be of the people, by the people, and for the people. Okay, thank you very much. This is about Abraham Lincoln. Okay, we will see you. Maybe I think we will shortly see or have offline classes. And luckily today, Laya is there before me, and she attended the offline class. Okay, so I think all of us will be together, and I will see all of your faces in the class, and I am really desperately waiting for that. Right? I
We do.
don't. Okay, so when you people are coming?
Sir, that's what we wanted to talk, sir. Like, we are coming on like in the first few days, no, sir. Monday, Tuesday,
Yeah,
Wednesday in the trains.
yeah, yeah.
Like, we can't attend classes while traveling, no, sir.
Okay, okay. Okay.
So, is there any chance to at least Monday and Tuesday? So that because most of the people are coming in the first 2 days.
Okay,
So,
okay. So because you will be on the travel or something like that.
I will be traveling and hostel fees and hostel allotments. Several things will be there, no, sir.
So you don't want classes on Monday and Tuesday.
Yes, sir.
Okay, no problem. Okay.
We can start directly offline classes from
Yeah,
12
yeah,
or
yeah,
next week, next week.
yeah, yeah. Okay.
Okay, sir.
So we'll see if all people come.
Yes, sir. Like
We'll just
Monday, it is definitely not possible
yeah,
because
yeah,
Monday
yeah,
is the first day.
yeah, yeah. Okay, as you wish. I normally don't try to force anything,
Yes,
right?
sir.
So whichever is convenient for all of us, we will have like that.
Okay, sir.
Okay. And how is the this mid exam? Any comments about that?
It's very lengthy, sir.
Yeah,
That's it.
it will be
Yes, it's
lengthy.
quite lengthy.
It
Like
will be lengthy.
really, really lengthy, sir. Not on the scale of 20% or 30%, like 200% lengthy.
Okay, okay. Let us suppose it is only four problems, not six problems. What is this?
Hmm.
Okay, don't worry about the average marks and all. And it is because I always see it is a relative grading, and it is like MBA exams or GATE exams or something like that, or JEE advanced. So nobody will answer all the questions, right? So it is like percentile. Whoever gets better, he will get better grade.
Sir,
That's all.
nobody will answer all the questions that I agree,
Yeah,
but
yeah, that's
in
what I
which,
told.
in which it's
See, in
like
a
I didn't answer
given
one
time,
question completely, sir.
see, given time, all people can do JEE, advanced GATE or MAT or CAT or anything, right? So all people can do all the problems. Only thing, the uh, the time only, right? So